So let's discuss friction with more detail now. So we said that friction has two types, or there are two types of friction force. One is the kinetic and one is the static, right? So if we call F sub F, we're going to say that one is static, which as the name says is whenever the object is not moving, and the other one is going to be kinetic, which is whenever the object is moving. So velocity is going to be non-zero, right? And the formula basically for friction we know is just simply mu times normal force, where modulus of the normal force if you wish, and then this is going to be, if you put a vector, it's going to be negative because it's going to be opposing the direction of motion that we typically take as the positive direction, right? Okay, so then it's just negative, it just opposes. Now this mu is going to be also mu sub s for static, and mu sub k is going to be for kinetic. One of the things that we know, because we observe that, this is telling us how much is the force of friction. So let's say there is an object, and it's a heavy one, for instance a fridge, right? And we're trying to push it. We're here pushing the fridge, and we realize that we could see that as we're pushing, as we start to push, right, we see that the fridge doesn't really move. And we have to increase our force up to a point where actually the fridge starts moving. So we could even say, like, we don't use plots, but the idea we can understand it in here is that we can see that we observe that as the force here, let's say, increases, we put more force, but there's no motion, and at some point the object starts to accelerate, right? So we observe that scenario. What this regime is happening, there's no motion, so velocity is zero. And in this regime, velocity is non-zero, right? It's starting to move. Let's call this velocity, right? So, or acceleration if you wish. At some point, the acceleration becomes non-zero. How do we justify the fact that even when we're applying a force, if we make a free body diagram, we're going to see that we're going to be applying a force which is us pushing, right? And if we analyze this object from the point of view from the free body diagram, we're going to know that the net force of this, which is going to be the sum of all the forces, is going to be equal to, well, where there is a positive push, and then we're going to have that that's equal to mass times the acceleration in the horizontal component. Let's call this, of course, the horizontal component, right? So in this frame of reference, we're saying we're pushing the object, but it's the object, the net force is going to be mass times acceleration, but the object is stationary at first. When I'm pushing and the fridge doesn't move, at the beginning is stationary, it's not moving, and at the end it's still not moving. So then I know that the change in velocity is zero, which means that the acceleration is zero. If acceleration is zero, of course, that means that the net force is zero. We see that immediately from Newton's second law. If this is zero, this is mass times zero, which is zero. So now I find a situation where I say push is equal to zero. And that doesn't make sense because I am actually pushing the fridge, right? So I make the effort and I'm in contact and I'm pushing and I can increase that push, but still acceleration is zero. So the net force needs to be zero. So how do I justify this phenomenon that I observe? How do I justify the fact that I am pushing an object, there is a net force, if at least I can think of there is a net force, or there's certainly a force applied in the direction of the motion, but that force is not producing an acceleration. That is because I need to account for something that counterbalances that. This is the same idea we discussed with the idea of normal force. We have weight, and weight is responsible for a pull vertical. But if I put the object on a table, the object doesn't fall. So I need to posit there is something that is counterbalancing that effect, or that, that force of gravity, and that's the normal force, which is the table, for instance, pushing on the object upwards, or if its tension is the string pulling the object upwards. This is something similar. Now I need to posit there is something, and that something needs to be opposed to the force, such as the object is zero. And what's that force? Well, that's a force that is opposite in motion, and that's friction. Because the object is not moving, I just call this a static friction. But it's again the idea of friction. So then I can see that indeed the push, or rather let's solve for friction. I know that the friction, static, right, it's equal to the push. So this is what I realize, because I need to justify the fact that the object is not moving, right? I am pushing, I'm certainly not doing a non-zero push, and still the object is not moving. And then I could see that at some point, as I increase my push, and this will be then the force of the push. I increase my push force, let's say 0 newtons, and then this is 1 newton, and then 2 newtons, and so forth. And at some point, suddenly the object starts moving. And at that point, I can also feel that the push, I actually need to keep it moving, and this is something that you can experience if you're trying to move a heavy object. You try to move the heavy object, it takes a lot of force. Once you overcome that reactive or this opposite force, which is static friction, the object starts to move, and then you actually need less of a force. That's because you have gone from static to kinetic force. So we can see that indeed when you're applying a push of 1 Newton might not be enough, a push of 2 Newtons, and we see that at a certain point there is enough. So what's that point over here? What's that force? Well, that's the maximum friction static, and that's actually given by mu sub s times normal force. So we're going to see in all these problems how the first thing that we always need to do when we are solving static and friction force is determine whether the object is moving or not based on the physics of the problem. Then the first thing we're going to have to do is find the normal force, and then we calculate the friction force, the maximum static friction force, which is going to be mu sub s times the modulus of the normal force. And then from here we ask, is the push larger or smaller than the friction maximum static? Well, if it's larger, then we're going to have a scenario where we are above here. So then we're going to have motion. So then we're going to have kinetic. So I'll go to my kinetic formula, right? I just put kinetic coefficient of friction and it works. If I have a push force that is smaller than the maximum static friction, means I'm not going to be able to overcome that reaction, and then I'm going to be here, which is where I have no motion. I'm moving in the static regime, right? So then I see that this is the explanation of the phenomena I observe. That's what we say. There's a sort of phenomenological definitions of the force. I'm making the force, I'm applying a force that otherwise I would expect is given motion, but it's not. Why is that? Because I have a counterbalancing force. What's that force? That's static friction. And then at some point I overcome that static friction, because the static friction, it has a maximum, and that's whenever I go from static to kinetic, and then I use kinetic friction. Now this idea is not that difficult to believe. We saw this similar also with elastic force. In elastic force we saw that there's 3 regimes: elastic, plastic, and inelastic. And at some point if you do too much of the displacement, right? So if we plot, in that case we were saying displacement and then a force, elastic force will be this one, which will be the restorative force, and this is the displacement I make. At first, when I'm making a small displacement, the force goes linear, and the constant of linearity is the constant of the spring. At some point, however, this doesn't go linear anymore, and even if I increase a lot the displacement, the restorative force is not growing much, which means that the object is not going to have enough force to recover itself, and so it's going to be deformed permanently, right? That was what we call the plastic. And eventually, if I pull too much, it just breaks. So we have elastic, plastic, inelastic. So this is the idea. Laws have a limit. So if whatever phenomena is acting, which we will see in a second, on static friction, is going to be overcome whenever I push too much. And this is exactly what we're saying. I push a little bit, it's not enough. As I increase, it's not enough, but at some point it just is enough. And that's whenever you have overcome the fundamental reason why you have a static force. Now, static and kinetic forces, friction, in any case, are usually, you can understand them as two fundamental reasons for that, right? In any case, these equations are just true in a first approximation. If you want in detail, you're going to have to come up with more complex models. The foundations for this comes from the 17th century, and even before even Da Vinci studied concepts of friction, right? This has been studied for centuries, and we just keep using it because it's functional in a first approximation. But of course, if you want to go into much detail, you need something more elaborated. We're happy with this for the same thing as elastic force, right? We're happy with this in physics 2053. Now, there's two ways that we can understand this, or two reasons that they're kind of combined. The first one is just purely geometrical or morphological. If we take if there's two objects in contact with each other, right? Let's say this is a table and that's the object, and I kind of zoom in this area. What I'm going to observe is that the surfaces are not really smooth, even if they look so to the eye. So maybe the object, it looks like this, the surface, and the surface of the other object of the table looks like this. And so what happens as one pushes on the other, right? Because this has some weight, and so this is going to offer a normal force, and that's the normal force I'm talking about here, right? That's the normal force that this object is going to experience from the table pushing. Of course, the object pushing on the table is going to produce a normal force downwards, and it has as the weight, right? So then I see here that the actual friction makes sense that it depends on the normal force. Why? Because normal force is sort of also telling you how much effective weight is acting on the other surface, in other words, how much is pushing against the other one. And so we can imagine that we have two surfaces trying to push each other. They're going to kind of imbricate together and get entangled. So the more that you push, the more that they, and then if you're trying to, the more they get linked. And then if you're trying to move it this way, we're going to see that you can, you're like, tick, 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 right? You can imagine like, boom, 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 the bumps crossing against each other. So it's going to be opposing the motion. That's one of the ideas of friction. Friction is just a morphology or a geometrical thing of the fact that the surfaces are not smooth. There's another second one understanding of this, which goes from the chemistry of surfaces, right? You can talk about two surfaces being in contact, and therefore there's going to be some bonds, chemical bonds in between the two objects. And so you have to overcome those bonds. And intuitively makes sense, both theories, because once you start moving, the object, maybe in this one less, but in the other one, adhesion of the two surfaces, the two different surfaces, as you start moving, the bonds that may form between the table and the other object, right? We can say, oh, there's maybe electrostatic attraction or something like that. You will study in physics too, right? As you start moving, you sort of break that. This is the example, for instance, of taking the spring and pushing too much. Well, the static force will be like a spring. You can deform it a little bit, you can push a little bit, and then this doesn't move, that will be static, but at some point you push too much, that breaks this bonding force, and so then the table is free to move. And that's why I see that if I go analyzing how friction works, let's say force, and this will be like a force applied, right? This will be the push, so to speak, and this will be friction. What I'm going to observe is that the first I need just to increase, it just increases the same, proportional, of course, to mu sub s, and at some point it's going to drop, and it's going to go like this, which is this regime, which is mu sub k, and times f sub n. That's going to be actually the value, right? That's the value there. And this is the kinetic, and this is the static. So, this is actually the other way. So this is the push, and this is friction. And so what I observe is the value of the friction goes matching whatever value I have on push at a point where it goes from the static regime to kinetic. Why? Well, because then there's no, maybe I'm pushing much more, and then there's no enough, I'm breaking those bonds, and so they're not adhered together, and then you're more free to go. And that's something that we observe in the kinetic. Friction always is smaller than static. I mean, it wouldn't make sense otherwise anyways. And that's because also we say that the kinetic coefficient of friction is going to be smaller than the static kinetic coefficient. These coefficients, which are the friction coefficient, right, these numbers are given to you typically in the problem, unless they're asking you to solve for that based on how the motion behaves. But again, this is the general idea of a static friction. Then it becomes the same. Once I know a static friction, I can just go and solve some problems, and then the problems are going to be solved the same way that we were solving problems without friction. Now we're just adding this layer of complexity into it. So let's see these concepts of friction, static and kinetic, in the context of this problem. In this case, we have the same box that we had before. The box is 10 kilograms, and they are telling us that the surface has a kinetic static friction of static of 0.4 and a kinetic of 0.3. Another question they're asking us is, there is a push, and we want to know in which case how much is going to be the friction, right? Now the first thing that we need to do, of course, in any problem is realize that this is going to be a problem of forces. We need to do a free body diagram and determine the things. So because it's a free body diagram, first we're going to start with the vertical component of the motion, for instance, and we're going to see that in a free body diagram, remember, free body diagram is just simply the object for which you are analyzing the motion, forget about the rest. So we're just taking the box in here. We draw our box and say what forces are applying vertically into this box. Well, for sure, if I get the box and I put it outside of the table and I let it go, that falls. Why is that? Because of gravity, so I know that there is a weight force, right? And that's pointing vertically, right? So that's supposed to be vertically. Okay, and then do I have any other force? Well, I would expect to have one, because if I didn't any other force, there will be a net downwards force, which means there's going to be a net acceleration downwards, it's going to be moving downwards, but the box doesn't go through the table. So that's why, because there is a normal force counterbalancing that. That's the force that the table does on the object. Okay, and so, okay, so then we can write the balance of forces, which is just the sum of all the forces. Remember, that's equal to mass times acceleration. So we can write the forces. What forces do we have? We have the normal force minus the weight force, and that's equal to mass times acceleration, right? That's the net force in y. Right, this is the net force, always the net force, okay? So then we have this scenario, and then we say, okay, what is the acceleration in y? Well, I know the acceleration is 0 because it's on the table again, it's not falling through the table, so that means this is equal to 0. So how much is Fn minus Fw? Well, then that's 0, which means that Fn it's equal to Fw, which is equal to m times g. If we replace the numbers, m is 10 kilograms, and g is 10, so that's going to be about 100, right? Newton. Exactly 100 actually. So the normal force is going to be 100 newtons. So we found the normal force. Let's go to the horizontal motion. So again, we need to make a free body diagram, and in this case, we're just having the object, and we analyze what forces are acting on this object. Well, there's a force, which is just simply the push. Is there any other force? Well, there's two objects in contact, and I'm trying to move this. So that's going to be friction. Unless I'm told to ignore the friction, in this case I'm explicitly being asked about friction, then I'm not going to be able to disregard. And so I have to put my friction. And whenever I do the balance of forces, I'm going to say what forces are acting positive, that's going to be the push. Which ones are going in the opposite direction, that's going to be the force of friction. And that's going to be mass acceleration in x. Now the acceleration in x, I don't know, I'll have to find out. But the basic idea here then is I have the push minus the friction force equals mass acceleration. And now we have to make this decision. Let's make it here and then we'll put it back here as a memory of this scenario. What do we have to do? Once we found this, we found the normal, we need to figure out what is the maximum static friction. And how much is that? That's mu sub s times the normal force. How much is mu sub s? 0.4. How much is the normal force? 100 newtons. So how much is correct? How much is the static friction? Well, the static friction is 40 newtons. Okay? So the maximum static friction is 40 newtons. What does this mean? That as I start pushing an object, static friction is going to be matching that force all the way up to 40 newtons. And whenever I put more than 40 newtons, like 41, 42, 43, doesn't matter, then the object is going to start moving. And at that point, I'm going to see, because the object moves, I need less force, and then friction force is going to be dropping because we're going to be starting applying the kinetic force. So I can draw this in a decision diagram, which basically says, if, this is how I choose, my push is larger than the maximum static friction, then motion is going to be non-zero, or in other words, acceleration is not going to be non-zero. I have kinetic. And how much is going to be the friction in that case? Well, that friction is going to be given by the kinetic formula, so that means kinetic times the normal force, and that's going to be equal to 0.3 times the normal force, which is 12 newtons. So every time I have a force larger than the maximum static friction, which is 40 newtons, the actual friction is going to go, sorry, this is not 40, this is, sorry, this is not 40, so this is normal force is 100 newtons, not 100 newtons, not 40, so this is 100, so that's obviously 30 newtons. So every time I'm having a force, a push larger than the maximum static friction, then the friction is going to go to kinetic, there's going to be motion. The motion is going to happen with a constant friction of 30 newtons. If I put 50, how much is the friction? 30 is kinetic. If I put 100, how much is the friction? 30. If I put 1,000,000, how much is the friction? 30 newtons. Excuse me. That wouldn't work because you only apply this loss whenever there's a small velocity, and that sounds like a huge acceleration. But anyway, in a first approximation, let's say, this is always going to be the case. Friction is going to be constant whenever you overcome the maximum static friction. But what happens when you're below that? What happens when the push is smaller than the maximum static friction, right? And I'm just inverting the notation, but it doesn't matter. This is the idea what we're interested in. Well, in that case, the push is not going to be there's not going to be motion, so acceleration is 0. There's not going to be a change in the state of motion, so I know I am static. How much is the friction in static? Friction in static is going to be equal to the push. Why? Because if that wasn't the case, then there will be a net force. If this is the same, this is 0, so AX is 0. But if this is not the same, then AX cannot be 0, because the mass is never 0. So then I see it. Excuse me. If the push is larger than 40, I will use this formula. Friction is going to be 30 newtons. If the push is smaller than 30, I could not say, let's say 20 newtons, I could not say 20 newtons minus 30, because that will be a negative force, which means like I push there, but in reality I go there just because friction is acting. That wouldn't make any sense, right? So what I need to say is whenever I'm pushing with 20 newtons, is push larger or smaller than static friction? It's smaller. So what's going to be the static friction? Equal to the push. So the push is exactly 20 newtons, then the friction is going to be 20 newtons. I'm going to have a balance, 20 minus 20, mass equals mass times acceleration, 20 minus 20 is 0, mass times acceleration is 0, which means acceleration is 0. And that's what explains this motion. So to answer these questions, of course, we will see that in the case of 0 newtons, in the case of 10 newtons, in the case of 20 newtons, in this particular case 38 and 40 newtons, the friction force is always going to be, is always going to be equal to the push. So we can write it here if you wish. Let's put it here. In summary, and we can immediately see what do we do in a problem with friction. We start, we find out what's the maximum, we find the normal. From the normal, we find what's the maximum static friction. From the maximum static friction, we have our decision tree. And then we say, push equals to 0 newtons. How much is the friction? 0 newtons, smaller than 40. So we're saying is push, let's write it here explicitly for this problem, is push larger than 40 newtons or is smaller than 30 newtons? If it's larger than 40 newtons, friction is going to be equal to 30 newtons, which corresponds to the kinetic. If it's smaller than 30, friction is going to be equal to the push. So, is push 0 newtons? Is 0 newtons larger or smaller than 30? It's smaller than 30. So how much is the friction? The same as the push. How much is the friction? 0. Second, if push is 10 newtons, how much is the friction? Well, is 10 newtons larger or smaller? It's smaller than 30. Therefore, the friction is the push. So the push is now, the friction is now 10 newtons. You see how it's increasing? If I say 20, how much is the friction? Well, 20 is smaller than 30, which means that the friction is equal to the push, which means it's 20 newtons. So you see the static friction is always increasing from 0 all the way up to matching the friction. And at some point, what I'm going to have 40 newtons. What happens when it's 40 newtons? This is larger or smaller? Sorry, this is 40. Is it larger or smaller than equal than 40? Now we can see why. If it's 40 newtons, I'm pushing with 40. Friction can reach all the way up to 40. And I'm going to have the balance of forces. So I'm going to say that the push minus friction is equal to mass times acceleration. If the force is exactly the same as the opposite force of the friction, then acceleration is going to be 0. So of course push is going to be equal to friction, right? So push minus friction is going to be equal to 0, which means that the push is equal to friction. So that's why I'm adding here the smaller or equal, to 40. So in that case, if the force is 40 newtons, that is not larger than 40, is smaller, so the force is equal to the push. So that's exactly what I observe here. The friction is the same as the push, it's going to be 40 newtons. And what happens if I say that the push was 50 newtons? Then I see, 50 newtons, is it larger or smaller than 40? It's actually larger. So how much is the friction? The friction is 30 newtons. And that's why I'm going to see that I'm going to have, in the balance of forces, 50 minus 30 is going to be a net 20 newtons, which is going to be the one that explains why it's accelerating. And what if instead of 50, I do 100, right? Let's see that I do 100 newtons. Well, in that case, the friction is going to be how much? 100 is larger than 40. Friction force is going to be 30, still 30. It doesn't change. This is going to be always the same for the rest of the motion. And 100 minus 30 is going to be 70 newtons. So now I understand why I'm going to have an acceleration of 7 meters per square second. Before, I was going to have an acceleration of 5 meters per square second. Now of 2 meters per square second. Now I'm going to have an acceleration of 7 meters per square second. Now it makes sense. I push much more. I push twice as much. I'm going to have a much higher acceleration, right? And this is what we're seeing over here. Important, just make your decision tree. Find the static maximum static friction, then for that you need the normal force. So first find the normal force, then find a static friction, write your diagram tree, and whenever you're solving the problem, figure it out. Which one should I be applying? Should I be applying the static? Should I be applying the kinetic? If it's the kinetic, it's always the same. If it's the static, it's always the same as the net force in the horizontal component or in the direction of the motion, not necessarily horizontal as we will see in other problems. So let's solve now problem number 2 in discussions. Now we have the same box, and now we're pulling, and we're excuse me, we're pulling with a force of 40 newtons that acts on an angle 30 degrees. There is friction, and we assume the coefficient of kinetic friction is 0.3. And they ask how much is the acceleration in here. Well, as always, we start step by step. First step is finding normal. So we're going to do a diagram of forces. Before we go for that, we realize we have a diagonal force. If we choose our axes as x and y, then obviously it makes sense that we say that the force, which is 40 newtons, then I can just say that the force is going to be F sub x and F sub y. How much is which one? Well, F sub x is going to be the component in the horizontal direction, and that's the adjacent to the angle, so SOHCAH-TOA, that means that's the cosine. So I'm going to have 40 times cosine of 30. How about the vertical one? Well, that's going to be this one, which is the opposite, so that means that's the sine, so that's going to be 40 times sine of 30. Now this is 0.86, and this is 1/2, so that's going to be 20, and this is going to be 35, something like that. Doesn't matter, approx. Okay, so that's 86, right? Yeah, 34 point something. Okay, so that's going to be the force. Very good. Now I can do my free body diagram. Let's go with the vertical. In the vertical component, I'm going to have an object that receives a weight and has a normal force. So I can write the equation and say that the normal force minus the weight is equal to mass times the acceleration in y. And now I know the physics, which again, physics is not applied mathematics. It's actually observing the world and explaining the world, and we use mathematics to be quantitative in our explanation. So what do we observe in here? That the object has a weight. We know that because the object and Earth are in there. But we see the object doesn't go through the table. That's because the table or the surface or the ground is pushing the object upwards. That's the normal force. And now we can say how much is the change in velocity vertically for this box. It doesn't change velocity, it's just not moving vertically at all. So the change in velocity is 0, acceleration is 0. So I know this is 0, which of course means that the normal force is equal to the weight. The weight happens to be m times g, which replacing numbers, the box is 10 kilograms. Right? So that's going to be 10 times 10, which is again 100 newtons. Easy numbers. Okay, so the normal force is going to be 100 newtons. Second step, horizontal. So what do we have? Oh, we're going to have a push. Oh, I made a mistake here. That would be in the absence of this force. So, good catch at home. If you have this, that will be the case. But I forgot that on top of these forces, there's an extra component of the force. Which one? Well, there's the force of the guy pulling upwards. So there's actually an extra component of vertical force, which is F sub y, if you wish. So actually, when I do the sum of all the forces, I'm going to have the normal force certainly, but I'm also going to have the vertical component of the force, which is going to be the vertical component of the tension, if you wish. Let's call this tension, right? And so that's going to be the vertical component of the tension, and now yes, mass times acceleration. This is still 0, so that now we're going to have the normal force plus the tension in y minus the weight is equal to 0. In other words, that the normal force is equal to the weight minus the tension. That kind of makes sense. The normal force is the force reacting from the fact that the object is trying to go through, but with what force is pushing the object downwards. Not just the weight, it's the weight minus whatever I'm compensating for the weight. This is sort of the apparent weight, as we were discussing, for instance, in the problem of the scale and the elevator, right? The apparent weight that the scale measures. Well, that's going to be the difference of the weight minus my friend pulling upwards, and my friend is pulling with 8, so that's going to be 80 newtons. So actually, the normal force is 80 newtons. So now let's go for the horizontal component of the motion, and in this case again we do the free body diagram and we just put the box, only the box. What forces are acting on here? For certain we have the x projection of the tension of our friend pulling, and that's going to be the tension in x component. What else do we have? We have two surfaces and in contact, and they're trying to go against the motion, so you're going to have friction. Now I've not been told anything about static friction, right? Well, let's write the equation first. So we're going to have the balance of forces is going to be equal to the tension in the positive direction minus the friction in the negative direction, and that's equal to mass times the acceleration in x. Now, do we know the tension in x? Well, the tension in x is 35. We just calculated that, so that's going to be 35 newtons minus the friction, and that's equal to mass times acceleration. Mass is 10, acceleration we don't know. And then we need to know how much is the static friction. Okay, so then let's go back and remember, how do we work with friction? Well, friction, if push, we call this push, let's say, the force acting in the direction of the motion is larger than the maximum static friction, then we have the friction is just simply mu sub k times the normal force. Right? That's friction, it's equal to mu sub k times the normal force. How much is mu sub k? 0.3. How much is the normal force? 80. So how much is the friction, kinetic friction? 24 newtons, right? If friction is smaller than, if the push is smaller than the maximum static friction, then friction is going to be equal to the push. These are the two scenarios. Either friction matches the push, or friction is equal to 24 newtons, nothing else, right? Nothing else. So how much is the tension here? 35 in the horizontal component, right? So the question would be, is 35 overcoming the static maximum friction? Well, we can assume it is. Why? Because we haven't been given any information on the contrary. If we had been given a mu sub s, then we would use that, and I'm pretty sure we haven't, so yes, there is no information, so let's make the assumption that indeed we are above the static friction, and then we have that kinetic friction. If they were giving us a static friction, and static friction was, for instance, 0.5, then it will be 0.5 times 80, that will be 40 newtons, our force is 35, so we will not be there, and then the acceleration will be 0. Because we're not being given that information, we're going to assume, this is of course ambiguous, we could say, oh, we're missing information in here. Because we don't have that, we can assume that this is moving, and then we use that, and we find out that we are in the kinetic regime, and so the friction is 24, and so we say this is 35 minus 24, and that's equal to 10 kilograms times a sub x. This is 11, and that's going to be 11 divided by 10, which is 1.1. So the acceleration actually is 1.1 meters per square second. That will be the answer. Now, this answer is assuming that indeed we are above the maximum static friction. What would happen if there's an ambiguity here? If the static friction was larger than 35, then this will be wrong. The object would not move. We're making the assumption that this is not the case, and that's why we can use a kinetic friction. Again, this problem is a little bit ambiguous as it is written. However, there's one option where even with the ambiguity of the problem, you would be able to find out that definitely this is not above the static friction. And what situation would that be? Well, take this case. Imagine that the tension was not 35, a different angle. Let's say that the tension in x component was 20 newtons, for instance, right? Let's see, here, a small box. Let's say if the tension in x was 20 newtons, as it is, for instance, in y. What would happen here? We would have 20 minus 24, right? Tension minus force will be 20 minus 24. So we would have the tension minus the friction will be 20 minus 24, that will be minus 4, and that will be equals to mass times the acceleration in x, which means that the acceleration in x will be minus 0.4 meters per square second. Okay? Let's make a asterisk here. Okay. In this case, my answer will be, whenever I have a 20 newtons force, I have 20 Newton. Obviously, the question is if that makes sense, right? Because that needs to come from here, and it's very difficult. But let's pretend, right, that was a possible option, right? And I found that the acceleration is negative. What is this telling me? It's telling me that I'm pulling this way, and the box somehow goes that way. And of course, that's not something that we observed. So then we have to remember that physics is not just simply applied math. We need to we use the math to express things that we observe experimentally. And this is something certainly we have never observed. This is something that is meaningless, right? We cannot obtain a negative acceleration, meaning an acceleration that opposes the force where I'm applying just simply because of friction, because friction is a reaction. Friction is a reaction of me pulling. So in the best case scenario, I'm able to move, but I'm able to move with less than the force excuse me, I apply, right? In the worst case scenario, I'm not able to move at all. But there's no world, that we know of, where you're applying a force in this direction and the object goes in the opposite direction because of friction. Friction does never overcome the force applied. It goes from 0 all the way to maximum static friction matching the push force. And after that point, it just drops to a constant value, which is given by the kinetic friction. But it can never overcome the push force, never. So this doesn't make any sense. So if we come to this point and we find that indeed acceleration is negative, we are going to be, we're going to know immediately that this doesn't make sense, that this is physically incorrect, and that means that the tension force is smaller than the kinetic friction force. If the tension force is smaller than the kinetic friction force, and remember that always kinetic friction force is going to be smaller than static maximum, right? I'm saying now that my tension is smaller than the friction. Tension is smaller than the kinetic friction, and I know the kinetic friction is smaller than the maximum static. But if the force, which is the push, is smaller than the maximum, I should be using a static friction. And so my friction force is not going to be given by kinetic, it's going to be equal by the push. And so actually, because this is the push, I would know that the friction would not be anymore 20 newtons, it would be 24 newtons. Or in the case that we're saying, correct. Excuse me, that the friction force will not be 24, it will be 20 newtons, because it needs to match the push. Because the push is smaller than the static friction, and how do we know that? Because the push is smaller than the kinetic, and the kinetic is always smaller than the maximum static, then we certainly know that the push is smaller than the maximum, and so we know that in a decision tree we have to be in this regime, and the friction becomes the push. So the friction will not be 24 anymore, it will be exactly the tension, it will be 20, and I will have 20 minus 20, that will be 0, acceleration will be 0, of course, because we're in the static friction domain, object is not moving. So this is the only case where this ambiguity kind of gets removed because of the obvious conditions of the problem. In the one that we've solved, unfortunately, we have certain room for ambiguity if we make the assumption that the object is indeed moving, then we can just directly use kinetic force. So this question we don't really answer, we just assume and then we solve. If we were assuming this and we find this sort of result, we know that certainly that our assumption was wrong. In this case, we do not know yet if the assumption is wrong. We assume it is not, and we have a result that makes sense. In the absence of static friction, will be a little more difficult to justify. But there is probably the question whether actually this combination of numbers is physically meaningful. That we would have to figure it out. But just anyways, just if only for the thinking process, makes sense to say, well, in this case, 1.1 meters under the assumption that indeed we are above maximum static friction. Otherwise, it wouldn't make sense. Acceleration will be 0 because we are in the static friction regime. So problem number 3 on discussions, it's about a skier going down a ramp, and let's say there's a guy here and going down, skiing down. The ramp has, according to this problem, 30 degrees slope, so theta, let's say, is 30 degrees. And then the coefficient of kinetic friction, it's 0.1. What is head acceleration? So what is head acceleration, right? So the question here, of course, is going to be the same as before. We have seen forces without friction that we have to decompose into dimensions, into the horizontal and vertical component, or at least into perpendicular components that we typically call horizontal and vertical. And then we just solve the kinematic equations in those. Now, the problem here, of course, is going to be the same. Now we know we have friction. So we saw this problem already with, not this problem, but a similar problem with a ramp and a block going down or going up. And then we observed that there's two ways that we could choose our axis of coordinates. And as always, you're going to have them like 90 degrees, normal to each other. But you can choose any two axes that you like, right? So obviously, one is just the traditional, let's say, where this is our axis y and this is our axis x. That's a frame of reference with an axis of coordinates that's possible. And another one that we can use, in fact, is much more convenient in this sort of problems, is actually aligning the axis with the direction of the motion. Because the question is the acceleration down the ramp, the acceleration is going to be in this direction. So we could just choose to set the axis in this direction that we could call x prime if you wish. And then, of course, y prime, it becomes immediately this one. There's another virtue of choosing this axis of reference, as you already saw, is that whenever we need to have normal force is acting perpendicular to the interface of the two objects in contact. In this case, it's going to be the skis and the ramp. And so in that case, or the slope, and so in this case, normal is going to be aligned immediately with the y, and then the acceleration is going to be aligned with the x. There's still the possibility of using this axis, but you're going to have to decompose. Weight is going to be aligned with the y, but the normal force is going to be perpendicular, and so you're going to have to use trigonometry to find out which one is the angle and then expose, but it doesn't matter because at the end of the day, this is basic trigonometry, so you're going to have a 90 degrees, so you're going to find the one aligned, right? But just remembering any triangle has 180 degrees total internal angles. One is always 90, which means that this one and the other one are going to be, in this case, this one and this one for the ramp, right? If this is 30, that's going to be 60. So it needs to be 90 minus that. And based on that, you can just figure out the rest of the angles. So in this particular case, let's choose the axis of reference, the axis of coordinates, that are aligned with the ramp and the normal of the ramp. And as usual, we need to find the acceleration, and we know that acceleration is given by force equals to mass times acceleration. So we need to find acceleration. In particular, the acceleration in this case is asked in the direction of the slope. Well, that's not explicit, but it's typically implicit. If not, we can always convert it. Once we find that acceleration, we could find acceleration in the y direction, and then just remember the acceleration is going to be the square. But of course, immediately we remember that this skier is not really jumping up and down, so the direction, the acceleration in y is going to be 0 anyways. So all the acceleration is going to be in this direction, which is something very convenient in compared to the fact where you have this axis where you're going to have to find the modulus of the acceleration by making the x component squared times the y component squared, and then the square root of that, again the modulus of the acceleration, right? So in this case, it's going to be much more simpler, and it's a good idea. Again, you can go and solve the problem with this one. It's a nice exercise, but just to elaborate it. So let's focus on this one. And we're going to call y is going to be our vertical and x is going to be our horizontal. So as usual, we need to just figure out what are the forces acting, and the forces in this case are going to be acting in the horizontal and vertical components, where these are x prime and y prime, right? So let's analyze the motion into horizontal and vertical components. So let's keep the axis as it is right now, and let's make this is our skier, and then we know what forces are acting in here. Well, we have, first of all, we have weight force in here, and then we know also, because the object is pushing down on the ramp, there's going to be a ramp component, there's going to be, a reaction of the ramp being a normal force, and this is W, and that's N for normal, right? Now, do we have any other forces acting on this object? Well, there is one more in this case, and it's the fact that the object is presumably going down, and so it's going to have a friction. And the friction is opposed to the motion, because the motion is going in this direction, right? We expect the motion to happen in that direction. We could just call that V in this direction. Then we know there's going to be a friction, and there's going to be a friction opposed to the motion in that direction. Again, friction is aligned directly with our x prime and y prime axis, which is another advantage of not using this one. Otherwise, we would have to again decompose friction. So there's many things to decompose. It makes just sense to decompose weight, which is 1, and keep normal and friction directly aligning to our new vertical and horizontal axis. Any other forces? Well, we don't have any other forces in here, so we can just now split this into the vertical and horizontal components. So in this case, vertical component is going to be y prime, and of course y prime is just this one, and this is x prime. So then vertical is going to be y prime, which is going to be weight. We can just realign things, and then we're going to have a component of weight of, normal. This is normal, right? This will be the axis. This will be y prime. So we're going to have weight, and we're going to have normal force, and then we're going to have weight. But what weight? Well, it's going to be the x component of weight down direction. And if we're going to go to the horizontal motion is going to be in the x prime, and the x prime direction, we're going to see that we have in the x prime direction, and we're going to observe we have the skier here. And what do we have in the x? Well, we certainly have the friction, that it's aligned, so friction is going to be going down, the force of friction. And will we have anything else? Well, we do have an x component, and the x component is that of the weight. In fact, this is the one that justifies, right? That's going to be y in x prime, and this should be, y prime. This is actually the one. Forget about the friction. If the object is falling downwards, it's because there is a weight into the component, into the direction of the ramp. If there was no component of weight in this direction, the object wouldn't move. In fact, you might see that sometimes you put an object in a ramp, in a slope, the object doesn't fall, and you say, why is the object not falling, right? So if I take, I don't know, a piece of paper or something like that, and I leave it here, and it's not falling. Why is it not falling? Well, certainly there's gravity going in down direction, which means there is a component down the paper, because if I remove the paper, the thing falls. So the weight is, the normal force now is not compensating for the weight. It's just compensating for the weight in the direction perpendicular to the interface. So why is this object not falling? Is because there is a a static friction that is preventing the motion happening down the ramp. So this is actually, there is a weight component, but that's not enough. I mean, this in case is going to be enough to make it move. Sometimes it's not, whenever this weight component is smaller than the maximum friction, static friction of the object in the direction of the ramp. Okay, again, remember every motion is going to happen whenever you have force into the direction of the motion that is above the maximum static friction of the object. So once we have this free body diagram, we can just solve the problem for vertical and horizontal components. We can make the addition of the forces and see what's the balance. Let's erase this and explicit it. Now before we explicit that, let's just recover the diagram in here. In this case, we're going to have normal force acting here, and then we're going to have a friction force acting here, and then we're going to have this is going to be x prime, and this is going to be y prime, and then we're also going to have a weight direction in here. And then we want to decompose the weight direction into the x and y, x prime and y prime components. So we know that this angle is 30. We saw this already in the previous one. So this angle over here is 90 minus 30, which is 60. And this is 90, so that's 60. 90 minus 60, this is 30. So now I find that indeed, we saw this already, this angle, what's the angle that the weight makes with respect to the, not the horizontal, in this case is the y component, is 30. So if I want to decompose the weight component into the x and y components, weight component is going to be given, instead of saying, if I say in the x and y components, which are the standard components, the weight is just going to be moving down, right? It will be like this is weight. So weight would be aligning here. And so weight would have non-zero component and just purely whatever mg going downwards. But now in my new components, this is x prime and this is y prime. So I have to decompose it in this axis. In this axis of coordinates now, I'm saying that the x component of weight in the x prime component is the side over here, and that's what? Opposite or adjacent, that's the opposite. So when it's opposite SOHCAHTOA, that's going to be the sine of the force. So it's going to be mg times sine of 30. And what about the x prime? Let's put here weight in x prime and weight in y prime. And so we come here and say weight in x prime is going to be what? It's going to be the force weight times sine of 30. What about the weight in the y prime component? Well, the y prime component is just this one, which is the adjacent, so SOHCAHTOA, so that's cosine. So it's going to be the modulus and then the cosine of 30. Now you can compare this example. The x component in the the weight component in the x prime is non-zero, whereas in the x with no prime was 0. The y component in the y prime component, it's non-zero, and this one is mg. Fw, of course, is mg anyways, right? This is mg purely. And you see how the components change. However, you do square of this plus square of this, you're going to find exactly the same as square of this plus square of this. Obviously, it needs to be the same force. So basically, when you decompose that, you're going to find, by the way, don't forget, this is positive because it's going in the positive direction, but this is negative because it's pointing downwards, so don't forget the minus. So now I can write, finally, the weight into the y prime component, and that's going to be given by, this weight force is going to be mg. We don't know how much is that, so let's keep it just like that. Mg times sine of 30, which is 1/2, and then that's going to be minus mg times cosine of 30 is 0.86, so let's say 0.86 with the minus. And so that just gives us the composition, of the weight in the xy components. So once I have this, we can go back and write the horizontal and vertical components. Let's write this thing here and solve for the problem. So now we can just write back the vertical, which in our case is going to be the y prime component. And so we have the skier again, we have a normal force acting in the y prime component, and then we have the weight component acting downwards, which is the y component, the weight component, right? In the y component, y prime component. So now we have the balance of forces. This is the net force into this direction is going to be mass times acceleration, which is the sum of all the forces, right? So what are the forces acting here? We're going to have a normal force minus the weight force in the y prime component, and that's equal to mass times acceleration in the y prime component. But we know that the skier is just going down, it doesn't go up and down in the y component, so we know it's not going to change its velocity there. This is going to be 0, which means this is 0, which means that the normal force is just simply the component of the weight into the y prime component, right? That's the weight into the y prime component, which is this component over here, so that means minus, without the minus, sorry, because we already had the minus there, so this would have been plus, but we go there, and so it's going to have 0.86 mg. And then I can go to the horizontal component, which horizontal now is going to be x prime. And so what happens in x prime? Well, it's going to be the same. Now we're going to write the skier. We're going to have what component in the horizontal? That's going to be the weight in the x prime. What is opposing that? That's opposing the friction. Now, how much is the friction? Well, we are moving. We're assuming we're moving. Therefore, the friction that we're going to be applying is the kinetic friction, not the static one. It's in motion. If it's in motion, it's kinetic. And what's the formula for the friction when it's kinetic? Right? Well, when it's kinetic, it's actually just simply mu sub k times normal force. Now, this is for kinetic, right? Which, of course, we are assuming because they're asking about the acceleration. So unless this force eventually it overcomes the weight component, we know that it is possible it's moving, so we take as a given that it's moving. So once it's, we can replace numbers, so mu sub k is 0.1, and the normal force is 0.86 mg, so that's 0.86 and then mg, and that's going to be 0.086 mg, right? That's the weight, that's the friction component. And how much is the x component? Well, now we can just make the sum of all the forces. So the forces in the x component are going to be mass times acceleration, and it's given by the sum of all the forces. First, the xy component, which is weight in the x prime component minus the friction there, and that's going to be equal to 0.5 mg minus what friction, which is 0.086 mg. Now, if you make the difference in here, let's maybe erase a little bit, or let's try to write it here. So if you make the difference of 0.5, if you make the difference 0.5 minus 0.086, that's going to be 40, let's put this 0.414, right, mg, and that's equal to mass times acceleration in x. So how much is acceleration in x? Well, masses and masses cancel, right? That's going to be 0.414 mg divided by the mass. Masses and masses cancel, and then the ax is 0.414 times g, which is, this is times 10, so let's say 4.14 meters per square second. Now, it's something very interesting in here, that 4.14 meters per square second. If there was no friction, this would have been 5 meters per square second. Now we have friction, so it's going to be 0.414 meters per square second. Important thing here, this does not depend on the mass at all. We kind of saw that already in the chapter without friction, but because there's friction, acceleration is going to be slower. Why is lower or lower? Because there's a friction acting against that. It's kind of opposing, there's a decelerating force. In the absence of friction, the skier will go 4.14. Potentially, when the skier was going at with the friction was high enough as to compensate for the total weight in the x component, the object wouldn't move at all, right? And the acceleration would go to 0. For that, you probably would need more data to check if actually you're already in the regime of static friction instead of the kinetic friction, meaning that your force, weight force in the x component was above or below the static maximum friction, right? Maximum static friction. But anyway, way to solve it, it's just exactly the same thing. We just add an extra force and keep doing the balance. There's nothing more in here. So problem number 4 is actually a very interesting one because it's a real-world application of the principles that we have studied. Forensic police that comes, for instance, to a traffic incident where there has been a collision that requires actually making a report, probably for the courts, right? We're going to have to study these ideas and try to figure out what happened. And you can figure out what happened based on the laws that we know. So in this case, we know there was a car, let's say it was rolling down the road. Maybe there was another car coming here at an intersection that maybe didn't have a clear priority because there were no signal, no light traffic, no main road and side road, right? And somehow they just came to collide. And maybe there was a witness that saw the scene and said, oh no, the guy in this road was coming to stop, right? And he almost stopped, but just barely. And then they just crash, right? And so the question is, who's at fault in here? And maybe the guy that came here is at fault, potentially, but this guy says, wait, I didn't yield because this guy, I made a stop, I came to stop and then continue, but this guy was too fast. And so if this guy actually was breaking the law by going too fast, probably in the course it's going to be at fault, right? Whereas if he was following the maximum speed, maybe he was fine. So the police needs to figure out who was actually at fault. Was this guy, was that one? Maybe. If there's something like real losses, they're going to actually have to figure out this one for criminal law, right? So it matters. So the car was coming to stop. The problem is telling us that this guy actually about came to a stop at the end. And it took him, how much time does it take? Well, we don't know. But what we know is that the skid marks on the pavement. And that's a telltale for the police. Why? Because when you press the brake pedal, excuse me, this is a button. When you press the pedal, the tire's gonna block, right? And then it's not gonna rotate anymore. It's gonna be locking. So you use friction from the pavement to come to stop. So actually you have translational motion where instead of rotating the tire is actually skidding through. And because of that, there is some degradation, and the degradation of the rubber ends up in here, right? And they say that the pavement and rubber kinetic coefficient is 0.8, which is sort of a higher number when you compare with others. Makes sense. We want to have roads that are sort of half kinetic, high kinetic, up to a point, of course, high kinetic coefficient, because then we can come to a stop. In this case, it comes to stop in 72 meters. If there is no friction, then you never come to stop, unless there's air friction. But drag in this scenario is going to be very little force to actually compensate, and we have not studied drag, so in this world there's no drag from the air, right? The cars are very aerodynamic. So the point here is the police, knowing how much distance it took to come to stop and knowing the coefficient of friction and the final velocity, they're trying to figure out what was the initial velocity. Now this is sort of a kinematic problem we saw in previous chapter, but now we're introducing the ideas of what were the causes of this guy decelerating, which is going to be known as friction, of course. And because of that, it's going to be able to figure out what's the velocity. So the initial velocity and see who is at fault in here. So let's start with every problem in this sort of thing by splitting into horizontal and vertical components and analyzing the balance of forces. Before we do that, though, it might be nice to see that this is going to be responsible for coming to stop. If the coefficient of friction is lower, if it was 0, let's say, there will be no friction, there will be no skid marks. This guy will go forever, not changing his velocity. If the coefficient of friction was infinite, then you will not be able to advance at all. Why? Because then the maximum static friction will be infinite, and no force is larger than infinite. Therefore, you will always be in static friction, meaning there's no motion, right? So the higher the number it is, the less chance that you have to actually advance. The lower it is, the less chance that you actually have to come to stop. When it rains, when it snows, when there's ice, this coefficient of friction is going to drop dramatically, which means that if it took you 72 meters to come to a full stop in normal conditions, when it rains, when it snows, when it is icy, it might take you twice, thrice, as much times, I don't know, you figure it out, right, to come to stop, which is the reason why you have to be slower when the conditions of the road worsen. Physics can save your life. So balance of forces in here. So we have the horizontal component, right? And we're going to see that the car has what horizontal components? Well, is there any force acting in the direction of the motion? Well, there's nothing going forward, but there's something going opposite. What's that? That's the friction. And so we can write equations here that the total force, the net force in that component is going to be the sum of all the forces. There's no force here, but there's friction force here. And that's equal to mass times acceleration in x, right? And then we also know the vertical component. We have the car weight, and we have a net force, a normal force pointing upwards. So the net force is going to be the sum of these forces, which is normal force minus weight force. And that's equal to mass times acceleration in y. But we have seen this a million times. Cars do not start flying, so they just always go at the level, so there's no acceleration in the vertical component. So that means it's equal to 0, which is another way of saying that the normal force is going to be equal to the weight. And how much is the weight? Well, that's always m times g. Well, in a level surface. If the surface has a certain angle, then we would have to decompose as we just saw in the problem before. So it makes it more complicated, but the principles still apply. So that's why the police can figure out many different scenarios, right? The forensic people. Okay, so we have the normal force equal to mg. So let's come back in here and analyze. This is actually what we're trying to be told. So what information do we have? If we put the kinematic equations, v sub 0x, a sub x, and t. Okay, so what information do we have? What's the initial position? Let's say there's two ways of doing this. You can assume this is 0 and this is 72, or the other way. It's up to you. But anyways, let's define this, the initial position as 0 and final position as 72. It seems to be much more comfortable to say that this is 72 meters, right? This position here is x, it's 72 meters, and here is x sub 0, which was 0. Now, what was the final velocity? They told us it's about 0. And what is the initial velocity? That's what we don't know. What is the acceleration? We don't know, but actually it's here. And what is the time? We don't know either, right? So let's leave it empty. Now let's come back here to the acceleration. How can we figure out the acceleration? We have that the negative of the friction, it's equal to mass times the acceleration, which means that the acceleration is going to be the friction divided by mass. But how much is friction? Well, with friction, we calculate the friction is given in kinetic friction, is mu sub k times the normal force. But how much is the normal force? Well, we calculate it over here, so that's going to be m times g. So what do we have? That the horizontal component of the acceleration is going to be minus mu sub k mg divided by the mass. Mass and mass cancels, mu sub k times g. We've seen this by now a million times. So we write in here mu sub k times g. These two numbers, by the way, we have all the numbers. We don't have time. Actually, time is missing. So that's negative mu sub k times g. And what about time? Time is actually missing. We don't have. So what equation do you use when you're trying to find velocity but you're missing time? The one that you use is, of course, that the final velocity square is equal to the velocity square initial plus 2 times a sub x delta x. And now we can replace numbers. V sub square is what we're trying to find. The initial velocity was, this is the other way. The initial velocity is the one that we don't know. The final velocity is 0. So that's going to be 0 squared. It's equal to initial velocity. We're trying to solve for that. Plus 2 times acceleration. How much is acceleration? Mu sub kg. Mu sub k is 0.8. G is 10. That's negative. That's minus 8 meters per square second. So we're going to have negative 8. And then the change in displacement, which is going to be 72. Very good. So now we have 0. It's equal to v sub 0 squared minus 16 times 72. This is negative, so that can go to the other way. So this is v sub 0 squared is equal to 16 times 72, which we're going to keep for the time being, not to check the solution, times 72. And then, therefore, v sub 0 is going to be the square of 16 times 72. Okay, so probably it's now time to check the calculator. And we find this is 33.9, so approximately 34 meters per second. So now the police can say that guys was going 34 meters per second. To try to make sense of that, we can convert to a unit that we all understand, which is kilometers per hour or miles per hour. That's up to you. So we could convert to that. So if we make the conversion, that velocity, initial velocity, can be given as 122 kilometers per hour. So that seems to be a high wave velocity. And in miles per hour, that's going to be 76 miles per hour. So depends on your state. This guy is kind of crazy. So if he came to a collision in a, as we were saying, like a suburban condition, this guy is guilty, is liable, and he might actually have to face some jail time to keep him away from society. We don't need more maniacs. How do we know he's a maniac? Because of physics. It tells us, right? Nobody runs 76 miles per hour coming to an intersection with no vision to actually see the other guy. So because of friction, we can figure out what happened. We can explain why it happened. We have a full description of the motion. That's why kinematic laws plus dynamics is what allows us to provide a full description of motion. And this is a practical application where how this thing is actually used in a real world scenario example. So problem number 6, it's there's a man cutting the grass, 40 kilogram lawnmower, so let's just make something like this. The mass is 14 kilograms. She's a lawnmower, so 14 kilograms. Constant speed is a force of and is pushing, the person is pushing with a force of 88 newtons directed along the handle. So, which is at an angle of 45 to the horizontal. So basically he's kind of pushing this way at a 45 degrees angle. And so we can imagine that the man is just grabbing this thing here, and then he's just here. Not bad. Going this direction, cutting the grass, yeah, I don't know about that. But anyway, right? And so they're asking us to draw the free body diagram, showing the forces on the lawnmower, calculate the horizontal friction for the mower, calculate the normal force, and what force, well, so there are several questions, right? So let's start with the beginning, which is just finding the free body diagram. We can probably put it in here. Now, it's a very important thing to notice is the question asked was the free body diagram for the lawnmower. So how do we figure out that? So let's go step by step, so horizontal and vertical. So first we can just make the diagram. Now this is your object, because I kind of draw this okay-ish. So then I'm gonna say there's a force acting here, I could say, right? Which is the same as grabbing the force and putting it here, because vectors have no position, so I could just write that vector in there. And that's going to be 44 newtons, no, excuse me, 88 newtons. Yep. And at an angle of 45, this is going to be 45, right? And what else do we have? Well, there's friction, because they ask later about friction, so we could just say the friction in how is friction acting here. So friction is there. What else are we going to have? Well, the lawnmower is presumably on the grass or on the ground. So that's going to be, well, first there's going to be weight, and then there's going to be normal force. And so we see how things are starting to get crowded, which is interesting why we just split into two motions. And again, we're going to use the standard x and y components here to describe our motion. Now you could orient this in whichever way you want to do, but this is the most convenient one. So when we do that, we're going to just make that there's two horizontal and vertical. So horizontally, we can just put it probably here. So horizontal components of the motion are going to be what? Well, you're going to have definitely a -1, which is going to be the friction. And you're going to have a +1. Which one is positive? That's the guy pushing. But not the entire force, but just simply the component of that in that direction. How much is that? Well, we're trying to find this side over here, right? And that one with respect to this angle over here. Important. It's making it says a 45 degree with the horizontal. Now we know that's the way of putting it if we're pushing this way, because there's no other way of making it, right? So 45 degrees. So that's what with respect to that angle. That's the adjacent. So that would be cosine. So we're gonna have there is the force of the man in the x component. We'll explicit that in a second. And what about the vertical? What about the vertical? Well, vertical is going to be, the balance of forces is going to be what? Well, we have normal force, we have weight, and here comes the thing, we have a component of that guy pushing, the y component, which is this one, which is the opposite of this angle, but how is that looking? It's looking down, so actually we're going to have to put the man the force of the man pushing, right? We can call this push, or we can call it F sub y going down. So let's do this then step by step. So horizontal components. So we make the balance of forces. Remember, this is all sum of forces is mass times acceleration in x for the total in x. So how do we do that? X, we have F sub x, which is the man pushing, minus the friction. And that's mass times acceleration in x. What do we know about vertical? Well, vertical, we're going to have the F sub y is the sum of all the forces as usual, mass times acceleration in y. So what forces do we have in y? Then this is the net, right? Net force, right? Ooh, I don't know what I wrote there, net. So vertical forces, positive forces, well, we have a normal force. Negative forces, we have the push in the y direction. So that's going to be man into, excuse me, that's not the net. So let's not write the net, not to confuse. That's the net. So let's not call it F sub x and F sub y. Or if you want, just put net and y and net and x. But F sub x with no net is the man. This is the man pushing. And this is also going to be the man pushing. Or the child, if the man doesn't want to make it a job. Okay, so F sub y, and then you have weight. And that's equal to mass times acceleration in y. Now we can replace then in here normal force. We don't know how much it is. The man pushing in the y direction. Let's take the force of the man. The force of the man is going to be 88 newtons. And we can write as a vector that, so what is the x component? The x component is the adjacent to that angle. So that's going to be so k to us. So that's 88 times cosine of 45. What about the vertical component? Well, that's going to be what? That's going to be the opposite, and that's going to be sine. So that's going to be so, right? So k to us, so opposite, that's going to be 88 times sine of 45. But once we make this splitting, we come back to the physical scenario. Is the x in the positive direction? Yes, keep the sign. Is the y in the positive direction? No, it's actually pushing down, so we add a minus there, which is the minus that we just introduced in here. So do not double the minus. So once we write that, we can replace. That's going to be 88 times of sine of 45. That's going to be 0.7, something like that, right? So 0.7 times 88, well, let's just keep it for the time being. Well, let's actually figure it out. So both actually are the same. This is going to be 62, and this is going to be minus 62. Why? Because sine and cosine of 45 is the same, 0.774 or something like that, times 88, 62. So we have the force of the man pushing, right? This is the push force, and this is the push force. And so we can get the components and write them here. In the y component is negative 62 minus the weight. The weight is going to be the weight of what? The weight of the lawnmower, not the man, right? So that's 14 times 10, which is of course 14 times 10, mg, which is 140, and that's going to be equal to the mass of the object, which is still 14 kilograms times the acceleration in y. But before we go forward, we realize how much is the acceleration in y? Well, we know it's 0 because it's just moving horizontally, so this is 0. So how much is the normal force? That's going to be 140 plus 62, which is 202, about 200 newtons. Once we have that, we can go back to the problem of horizontal component. Now we know the man pushing horizontally minus the friction is going to be equal to the mass times the acceleration in x. How much is the force in x of the man pushing? 62 newtons. How much is the friction? The friction is going to be mu sub k times the normal force. The mu sub k is given us we don't know. And mass times acceleration, mass is going to be 14, so that's 202. 14 times the acceleration in x. Now at this point we have to incognita, so we can just write 62 minus mu sub k times 202 equals to 14 times ax. And we only have one equation, so of course this is non-solvable. Is there anything else that we can read from the physical scenario here? Well, from the wording of the problem, it says it's pushing a 14 kilogram lawnmower at constant speed with a force of 88. So as soon as we see that expression, we should have written somewhere, I didn't, constant speed, right? right? Constant speed, constant velocity means that the change in velocity is 0, which means the acceleration in the x component is 0. So in this case as well, this lawnmower is 0. So then we have that 62, this is equal to 0, excuse me. So when we have the 62, it's equal to mu sub k times 202, which means that mu sub k, let's write it in here 1 second, mu sub k it's equal to 62 divided by 202, which is going to be about 0.3. Right? And so we see the solution to part, I think this is part B, correct? We find the coefficient of friction, and then we can actually find the friction. The friction is going to be 0.3 times, over here, 0.3 times 202, which is going to be 62. Again, it needs to be the same. So friction, force of friction is 62 newtons. Coefficient is 0.3. Again, that's how we figure it out. Well, because it's moving with constant velocity. This is a beautiful example. Why is it a beautiful example? Because it tells something that we say many times, but now we see in action. First law of inertia of Newton, which is the principle that Galileo already expresses, says that an object does not, we said, common sense says, objects move only when you push them, otherwise they remain at rest. The natural, there's two assumptions in there. Natural position of an object is being at rest, velocity 0, and only when you put a force, the object gets in motion, right? But then we saw all the historical issues with that and all the counterexamples of that not really working well. Then came Buridan with his idea of impetus, and finally Galileo with the idea of inertia. And then the final definition of Newton's first law of inertia that says that an object will remain stationary or moving with constant velocity unless a force acts on it. Is there any net force acting on this? No, because it's moving with constant velocity. So what is the acceleration? 0. Are there forces involved here? Yes, but there are no net forces. But there are not net forces doesn't mean that there is no velocity. It means there is no acceleration. But moving with a constant velocity is 0 acceleration, but it's essentially not 0 velocity. So this is a perfect example of that scenario. We're seeing the guy is moving with constant velocity. He can do so because he's pushing exactly the same amount that the kinetic friction is acting against the object. And because of that, he maintains 0 net force in the horizontal direction, and that's 62 newtons, compensating for the 62 newtons because of the friction, and then the object moves at constant velocity. Now, we can just solve the problem then, calculate the normal force exerted vertically. Normal force is 202 newtons, and then that's going to be answer C. And then there's the last one, which we can do, we'll erase in a second, which is the question is, what force do you do to make it accelerated from rest to 1.5 meters in 2.5 seconds? Let's quickly solve that one. Now, part D asks what's happened, how can we make the object go from initial velocity of 0 to a final velocity of 1.5 meters per second in a time of 2.5 seconds. So what is this telling us? This is telling us acceleration. Why? Because acceleration is change in velocity over time. So change in velocity is of course 1.5 over 2.5, and that's 0.6 meters per square second. And the question is, how do we make, what force does the guy need to make such that you go with 0.6 meters per second, assuming that you have the same friction force. And this is important because if the friction force is not the same, then you may be open to have to recalculate the friction force with the new push. They're telling us the same friction force. We found that the same friction force was 62 newtons, right? That was what we calculated before. So then we can just analyze the horizontal motion and say that the net force in horizontal, like the sum of all the forces, which is going to be what? Positive force, which is going to be the man pushing in x component, minus the friction force, needs to be equal to mass times acceleration in x. How much is acceleration in x? Well, let's go step by step. What's the man x? We don't know that, as we're trying to find out. Minus the friction is 62 newtons, and that needs to be equal to mass, which is 14 kilograms times 0.6. And this is 8.4. So that's going to be 8.4 newtons. And so we can go there and say, what's the maximum force that the man needs to make? 70.4 newtons. This is assuming, again, that you have exactly the same friction force. This is reading that you can make of the problem. Otherwise, we'd say, like, you have the same kinetic friction force, and then you would have to recalculate normal force, because then you have an extra component, right? Because if you say, oh no, I have to push more horizontally, then the net force is going to be different, so it's not going to be any more 88 newtons, whatever, right? It depends on what the problem says. You can play with this. If you make this interpretation, the friction force is given is always 62 newtons, always. In this case, 62 newtons. How much you need to add? Well, you need to apply a force of 70.4. So we see now The force is 70.4, before was 62, now we have enough newtons left to be able to accelerate the object. As the object was 62 newtons, that matches friction force, and then you cannot change acceleration. Basically, acceleration is 0, and so you don't change velocity. Now we're changing velocity. How do we change velocity? Because we need a net acceleration, a net force. How do we produce a net force? By putting a force pushing, which is larger than friction force, and the difference of those is going to be giving you the value, giving you the acceleration that you were looking for, right? So again, step by step, split the forces, and then write the two, if there's kinematics in there, make the balance of forces, find net forces, and then solve the equations. It's always the same. Whenever there's friction, we just add an extra point, and there's just an important question mark is there seeing, are we moving with constant velocity or not? Important thing to figure out whether acceleration is 0 or not. Typically, vertical motion is 0. Typically, depends on the particular scenario. And then whenever we have friction, we're just adding an extra force for the balance, but the rest is exactly the same thing. So that's the last thing that we could say in here is that this is the x component, and what will be. And if you remember, we said that the force of the man pushing is actually F sub x and F sub y, right? And we just found F sub x. But how much is F sub x was the force of the man times what? This is the cosine, because, excuse me, that was the cosine because it's the adjacent. So that was cosine of 45, and that's what we're saying now it's equal to 70.4. So how much force does the man need to put? Well, 70.4 divided by 45, that's actually pretty convenient, because that means that's going to be man is going to be 70.4 divided by cosine of 45, and because this is about 0.74, that we can say that this is approximately 100. So if you want to find the total force of the man, that's going to be 100 newtons in this direction, or you can say 70.4 in that. How do you achieve 70.4? Because now you're pushing more downwards. There's a problem here, of course, if you're pushing more downwards, potentially normal force is going to be also, this component is also going to increase. It's going to go to 70.4. So in the balance of forces, normal force might change, but anyway, this is a solution proposed. We can just keep it. This part is probably less reliable, but this certainly is true. We can always make sure that this, then we see what are the consequences down the line.